Okay, one thing I started doing this past fall, at least in some of my courses to try it out, is recording the lectures, which works out pretty nicely if you miss a class or, well, yeah, basically if you miss a class, including if you didn't just feel like coming or something like that. It kind of makes it into a semi-distance learning kind of thing if you want, except you have to be here for the labs, which is like half the time. The thing that's a little different this time compared to last fall it was a larger group, and I like to use a classroom with a larger group and the computer is hardwired in. With a smaller group like this, we can get away with running the class in the lab, which is convenient in a couple of ways. But one way it might be inconvenient is this little computer here is connected to the network wirelessly instead of being hardwired in, which means if the network gets really busy, I'm not quite sure what's going to happen. I just looked at I taught another class starting at 12:20, and it wasn't too bad, but the picture kind of breaks up a little bit sometimes. I'll be walking around and all these big squares start forming on my shoulder, and there wasn't anything that was so bad that you couldn't see what was going on, though, and we're not exactly going for George Lucas type cinema quality here, so as long as you can see what's going on, I guess that's good enough. But if I start getting any complaints about the quality of the videos, we'll just move to a classroom where it'll come out better. But we're going to try it out in here like this. The videos will be posted in Blackboard. That is the only thing I use Blackboard for. Okay, all of the other materials I have posted are at a different website. I'll get to that. Let's just, well, I guess the main thing is to explain about how I do the homework. The textbook, I'm going to close that door. The textbook is a free textbook. If you want to read it off of a computer screen, you can just go to the website that's written there on the syllabus, and you can, I think it's a PDF or something like that. You download it. And if you want a hard copy of the book, you can buy one through the college bookstore or order it directly from the publisher, which might actually be a couple dollars cheaper. I'd have to check. As textbooks go, it's not terribly expensive, the hard copy, but well, anyone who wants it, most of you probably already have it, but that's the story with the textbook. The only thing you need the textbook for is to study from. To be honest, I don't think it's the best textbook I've ever seen, but the whole free thing seems to be popular. Any feedback you might have about the book, let me know. But the written homework assignments are all in handouts. That way well, that's what I've done anyhow. In the syllabus here, the first 5 pages are all the stuff that's supposed to be in a syllabus. The course description, the grading system, all of that kind of thing, my contact information. Starting on page 6, there's a few introductory paragraphs, and then it says section 1, electric forces and fields, which is what I'm going to start talking about in a few minutes. Reading, it tells you which parts of the book correspond to what I'll be going over. And then it says quiz A, and there's 3 questions. And then it says quiz B, and there's 2 questions. And then it says quiz C, and so on. That's the written homework for the first unit of the course. The course is divided into 14 sections, 14 assignments. I do not collect homework in the sense of coming into class and saying, pass it up, and going and looking at your homework, because on the few occasions I've tried doing it that way, you know, you get 3 papers that all have the same arithmetic mistake. That's one person doing the homework and 2 of their friends. What I like to do instead is quiz you on the homework, collect it out of your head instead of collect it on paper. So quiz number 1 The schedule is on the first page of the syllabus, right in front where it's easy to find. And I usually pretty much follow the syllabus or follow the schedule on the syllabus unless there's a snow day. Well, when would that ever happen? Actually, this time around, if possible, I'll try and get ahead of schedule, just simply because next year, the college is going to a 15-week semester like every other college in the world has, except for those who have a 14-week semester. And see, we've traditionally had a 16-week semester. So if I can figure out how to fit the course into 15 weeks this year, I've got it all worked out for next year. So if I get a little ahead, that's not a bad thing. But if anything changes, I'll give you a revised schedule. I'll write something I can hand it out. In the absence of any other information, keep your eye on that schedule there. Well, anyhow, it says a week from Wednesday, 9 days from now, it says quiz number 1. What that will be is one of the 5 questions, or one of the 5 quizzes, quiz A, quiz B, quiz C, one of those that I was just pointing out to you, except I will change the numbers so that you can't just look at it and say, oh yeah, I remember this one, the answer was 2.9. Well, now I've changed the numbers and the answer is 7.4 or something else. But aside from changing the numbers, it'll be the same questions that you've already seen when you were working on the homework. If you get stuck, I mean, the answers, at least to the problems, the answers are written right under the questions, but if you can't get it to work, or if you want to check your answer to one of the short conceptual questions or something like that, I have complete line by line written out, how did I get the answer type solutions at the website that's up here near the top of the page. Okay, page 6, 3 or 4 lines of other stuff, and then there's a website that starts out faculty.genesee.edu/my-name, and you go there. And not only do I have all of the solutions to the homework, but almost all of the other materials for the course also. If you're working on your homework on a Sunday night and you can't find your formula sheet, and of course on a Sunday night you can't ask me to give you another one, well, it's on the website. You can just bring it up on a computer or probably your phone and look at it. The lab book, everything is on that website, everything except the videos, which, as I said, those will be in Blackboard. But I kind of like having all the other stuff on a site that's not password protected. I already sent it to somebody this semester that said they were going to miss the first class. So you work on the homework. If you get stuck, you look at the solutions. You come in a week from Wednesday. I pass out one of those 5 quizzes. If I asked you all 5 of them, it would take like 2 hours, So just pick one at random. And that's what the quizzes are, quizzes on the homework. Roughly once a month, there'll be an exam, which, unlike the weekly quizzes, is not just recycled questions out of the homework. There's also a final exam at the end of the course that covers the whole course. And every week there's a lab. Labs are 10 points each. At the end of the course, I just add everything up. There's no complicated weighted averaging or anything like that. A point is a point no matter where it comes from. Losing a point on a lab is the same as losing a point on the final exam. So that's not everything it says in here. In any course, not just mine, you should read through the syllabus because the syllabus is the rules of the game. This is actually a legally binding document. If I do something that contradicts what it says in here, you can take me to court. You can take the college to court. So in any course, you should take a good look at the syllabus, but that's how to get through the next few days anyhow. Today, I'm going to make you sit there and listen to me while I go on and on about electric fields, things like that. Day after tomorrow, we will do our first lab. A week from today is a holiday, Martin Luther King Day, so don't bother trying to come to class because I'm not going to be here. Neither will anybody else. And then by 9 days from now, you should have worked on the homework enough so that if somebody just hands you, well, not only the questions, but the other thing is this other handout that was in this pile here, that's your formula sheet. This is your friend and companion. You get to refer to this on any kind of a test, and it's also a useful reference when you're doing labs or homework or anything. So based on the formula sheet and a slip of paper with the questions on it, if you've gotten yourself so that you can do the homework when you're at home, you ought to be able to do the same question when I hand it to you here in class. That's the theory. In practice, yeah, some people get 10s on the quizzes, but anyhow, that's at least part of how I run the course. As far as what all the rest of this stuff is, that pile there is the lab book, the thick one. That's the directions for every lab in the course, okay? It's a good idea to look those over a little bit ahead of time for a couple of reasons. So you might want to look over lab 1 between now and Wednesday. I already mentioned the formula sheet. That's the syllabus. And then this one is an outline of my lecture notes. It's not everything. What I typically do is, if I want to do a sample problem, I'll print up the question ahead of time, because that's not really the thing you need to focus on. But I'll write out the answer up here, because sitting there and copying it down kind of makes you focus your attention on what's going on, as opposed to just flipping through PowerPoint slides where, 10 minutes you're asleep. So I think it's a good idea to give you something to do during the class, like take notes, even if that is a little on the primitive side today. Well, speaking of primitive, I have here, you may have seen one of these in a museum somewhere. This is an overhead projector. There's the first page of the lecture notes.
We used those in public school when I was in kindergarten. I still have one of those. We were rebuilding the stage in the church where it used to be, and I had it it was last summer, and I crawled under there, and there was still one of those sheets that never fell through the cracks.
Well, they asked me years ago if I wanted this place converted into a smart classroom like all the others, and I basically said, "What for?"
Yeah.
But I admit it, I'm a dinosaur, but in my defense, I always just say, ask any 7-year-old, dinosaurs are cool, right? So, but, converting this, yeah, sure, it's all grant money, but still, converting this to a smart classroom would have cost a large amount of money. And aside from that, it would have taken away my chalkboard. I hate dry erase markers. So anyhow,
That's smoking.
well, I just put it. You'll stop.
Okay.
I just put a new bulb in it. Apparently, there must have been some dust or something on the bulb, because just before this class, I tried to start it up in my previous class, and there was a problem with the light bulb, and I have a spare projector in the back that I wheeled out quick and did the other class with, but I just put a new bulb in that. So yeah, it could smell until it's a little oil or dust or something. Once it burns it off, it'll be fine. If you actually see any open flames, that would be a problem. Okay, so this is the first page, and if you can't see it too clearly from where you're sitting in the back, all I really wanted it there for was something to point at while I talk, but that is just a copy of what you've got in front of you on one of the handouts I gave you. So if you're nearsighted, look at this. If you're farsighted, look at that. Much of this course is, as far as the subject matter, quite a bit of it is about electricity and magnetism. That gets us through the first 8 sections. The course has 14 sections altogether. The stuff on the third exam, I'm starting to be able to smell it over here now. Stuff that's on the third exam is waves and optics and interference of light and that sort of thing. And right at the end of the course, we spend a couple of weeks kind of on an introduction to atomic and nuclear physics. But any course where I cover electricity, I always started out with this little demonstration. I think I need to move this thing down if it's going to show up. There, that's going to be good. This might actually show up better in the video than it does from where you're sitting, because the camera's a lot closer than you are. Our modern words for electron and electricity and things like that come from the Greek word for amber. You know, that kind of orangish, semi-precious gem. It's fossilized pine tree resin is what it is. More than 2,000 years ago, somebody in Greece noticed that if you take a piece of amber and rub it on some fur or some cloth or something like that, that you will then be able to pick up little pieces of lint or small bits of leaves or things like that. And that was basically the discovery of electricity, and that's the story of that. This thing hanging on the string here is traditionally called a pith ball. Pith being sort of a cork-like substance from trees. Well, maybe more like vines than trees, but well, anyhow, this isn't real pith. It's just some lightweight plastic that's been painted with a little bit of graphite, but they still call it a pith ball. So I've got this plastic rod here because plastic is a lot cheaper than amber, and I rub it on the fur a couple of times, and then I touch it on the hanging ball. And the thing to notice, if I hold it up, you can see a little better. The ball really doesn't like that rod anymore at all. Now, I have over here a glass rod. And this one is actually real glass. And I've got this piece of silk. And I rub it on that a couple of times. And whoa, that was attracted, or it wasn't until it touched it anyhow. Now everything's discharged. Yeah. Okay, well, it was attracted at first. If you got a good look at it, it kind of scooted right over and touched the rod, but after it touched it, now it's repelled by the glass rod, but until it touches it, it was attracted to the plastic one. Now it's repelled by the plastic. Well, anyhow, based on these types of experiments, people figured out a long time ago that there are two kinds of electric charge. Okay, the terminology that grew up around this kind of thing is that what I just did to this was called charging it. And apparently there are two kinds of charge, because that rod is repelling the ball, but this rod is attracting the ball. So two kinds. It was Benjamin Franklin who came up with the names positive and negative for them. The like charges repel, because see, when I first started out, the way that ball got charged was by touching the rod. Some of the charge that was on the rod jumped onto the ball, so they have the same kind, okay? And when it's the same kind of charge, they repel each other. Opposites attract. So that much has been known for a long time. Some of it as far back as 2,000 years ago. Some work was done in the 16 and 1700s, but a complete explanation for what you just saw is only about 100 years old, because it involves the structure of the atom. Oh, almost forgot. This is why I write myself notes. A copy of the textbook. If you can't afford the free textbook, or the library has gotten in the habit of getting copies of the textbooks for a lot of courses and having them on reserve. So An option you have with the textbook, if you want an actual physical copy to hold in your hand, is they have one at the circular. You can't take it home, but it's on reserve. You can check out a copy of the textbook in the library also. Anyhow, back to our story. The structure of the atom is now known to, in some ways, resemble the solar system. Just as you've got planets orbiting around the sun, held in their orbits by gravitational attraction to the sun, electrons orbit around the nucleus of an atom, held in their orbits by electrical attraction. Electricity in an atom plays the same role that gravity plays in the solar system. Now, the outermost electrons in an atom are not particularly tightly held. It's actually pretty easy to knock one or two of them off. For one thing, this is kind of what chemistry is all about. Many of you have maybe taken a chemistry course, and you know they're always talking about this atom gives an electron to that atom, or this atom shares a couple of electrons. That's how chemical bonds work. Well, electrons can not only be exchanged between atoms by some kind of a chemical reaction, but just simply basically by mechanical friction. If this fur was all soaked in red paint, and then I went like that, should probably do it in front of the camera. Now there'd be red paint smeared all over the rod. Well, in a kind of a similar way, if I go like that, now there's electrons smeared all over that rod. And so that accumulation of extra electrons makes the rod negative, where it was neutral when I started out. Well, when the ball was neutral, some of the electrons jumped off of the rod onto the ball when it touched it. Right now it's already charged, so it doesn't want to get anywhere near the rod. One advantage to taking the course now, by the way, instead of if you wanted to take it in the summer, yeah, we're doing all this stuff the first week in July, the most humid part of the entire year. And these electrostatics experiments we do the first couple of weeks are sometimes problematic, to say the least. Right now, nice and dry, works beautifully. Anyhow, that's what the first part of this is about. The particles making up an atom are electrically charged. Protons in the nucleus, electrons orbiting around it. So I guess one of the things I'm trying to go over here is just the idea of what is electric charge. Electric charge is simply a name we've given to a property of elementary particles. Little tiny particles like protons and electrons and their various relatives. There are several numbers associated with these particles. We give them names like mass and angular momentum and stuff you've never heard on, like baryon number. And one of these numbers has been given the name electric charge. And you can tell if a particle is charged because it will push or pull on other charged particles. And there really isn't any better explanation than that for what charge is. Macroscopic objects, like this rod or some balloon you want to stick to the ceiling for somebody's birthday party, they become charged by gaining or losing electrons. Okay, I transferred electrons from that fur onto this rod. Those extra electrons gave it a net negative charge because electrons are negative. Now here's a point that catches people sometimes. The positive rod. Put a question on a test, and one thing that can bring out my red pen is if I ask somebody to explain how this thing became positive. Well, somebody's sitting there and they think, well, this gained electrons. Electrons are negative. That made the rod negative. If this was positive, protons are positive. It must have gained protons. No. The protons are buried down in the nucleus. The amount of energy needed to pull a proton out of a nucleus is something like 1,000,000 times as much as the amount of energy needed to remove one of the outermost electrons. For ordinary materials, like you've got laying around your house, at least the things I hope you have laying around your house, the protons never go anywhere. Something becomes positive by losing electrons, not by gaining protons. The exception would be if a certain type of radioactive decay is involved. If you have a piece of radium or something like that laying around your house, uranium, anything, yeah, then you do have positive charge escaping from the nucleus in the form of what are called alpha particles. We'll look at that kind of thing a little bit right at the very end of the course. But assuming that you're not trying to build a nuclear reactor in your garage, actually there was a kid that did that once in the 1990s. You've heard that story?
Yeah, I heard that. It took all the stuff out of the smoke detector.
Yeah, americium, yeah.
Yeah.
And thorium lantern mantles. And one day he hit the jackpot. He was poking around an antique store and there was an old clock that had a bottle of radium paint for the numbers on the dial sitting in the bottom of it. He took it all back and threw it in a big lead vessel. And yeah, imagine living across the street and peeking out through the blinds at all these guys in hazmat suits swarming all around your neighbor's house.
What about radon gas?
Radon gas? Well, this is actually a conversation for the end of the course, but since you brought it up, radon gas is part of the decay sequence that starts with naturally occurring radioactive. Uranium has a half-life of 4.5 billion years. Uranium-238 does anyhow. And so there's still some left over from the formation of the solar system, buried in the ground. And uranium decays into thorium, and thorium decays into, I forget what else, and that decays into radon, and eventually you end up with a stable isotope of lead. Well, the thing about radon that's different from all the other steps along the process is that it's a gas. All the, things like thorium are solids, and that makes it mobile. And it'll seep up out of the ground. And if you've got a nice tight house built in an area where there's a lot of radioactive material and the ground underneath it, it'll get caught in there. And so radon is the #2 cause of lung cancer behind smoking. Because if there's always, you see, radon only has a half-life of about 4 days. It fairly quickly decays into, I'd have to look it up. Might be polonium or something like that. Whatever it is, it's a solid. If there's always radioactive gas in your lungs, you are constantly coating the inside of your lungs with a radioactive material. This is unhealthy. And anyhow, I digress.
We have it in our basement, so that's fine.
Well, the way they mitigate that, it's going to cost you a few $1,000s, but they just install. Exactly, yeah, they put a bunch of, I don't know if you want to call them fans or blowers, but you just keep sucking on the gravel underneath your basement to create a negative pressure under the floor so that the air in the house diffuses downward instead of the gas in the ground diffusing upward. And if you don't do that, you'll never get a mortgage on that house because no bank wants to be stuck with a house that nobody can live in.
Yeah, they told us we didn't necessarily have to get one. No one lives in the basement, and then our house is like 200 years old, so the basement's really drafty, but they told us you don't have to go on. That doesn't mean anything.
Well, back to this stuff. I think we got down to about here. So I talked about lights, repel, and all of that. The unit for electric charge, it's measured in something called a coulomb. Now, for those of you who took the first course with me, I usually at this point explained the definition of a unit in terms of other units I'd already introduced, which went eventually back to the 3 base units, the meter, the kilogram, and the second. Well, the meter, the kilogram, and the second are all you need in mechanics. But the SI system actually has 7 base units, not just 3. And we're going to, well, actually, the SI system has recently been updated. This is the current way of doing things. Let's say the Coulomb is a 4th fundamental unit, defined not as a combination of other units, but rather the Coulomb is defined by the charge of the electron. So you go into a laboratory, you measure the charge of an electron, you multiply it by some very large number of electrons, something times 10 to the 18th power, and that much charge is a Coulomb. Okay. So basically, the amount of charge on something is proportional to the number of electrons that have been transferred. If I do kind of a job, like, transfer a few electrons, I give the rod a smaller amount of charge. If I do a better job of charging it, that transfers more electrons, I put a larger amount of charge on there, which would be reflected in the fact that a stronger charged rod would push harder on the pith ball there on the end of the string. More charge creates a stronger electric field around it. Stronger field will create more force on some test charge like this thing. I'm getting a little ahead of myself there. Charge is measured in coulombs. Charge on one electron is that little tiny fraction of a coulomb, and we'll consider measuring the charge of an electron to be the basis of defining the coulomb. Charge is to electricity what mass is to gravity. If you have a planet, well, you compare the Earth and the Moon. The Earth is a more massive planet than the Moon is. The Earth has a stronger gravitational field around it. If I had 2 of these rods, and one of the rods had more charge on it than the other, the more strongly charged rod would have a stronger electric field around it. Okay, so here's where I go over some familiar looking stuff for a minute. When we set up the current version of these courses in 2005, I think it was, it seemed as though it might be convenient if people could take the courses in either order, or maybe even take the second course without ever taking the first one at all. But if you're going to do that, you have to review a few concepts from the first course that carry over into the second course. So for the benefit of anybody who has not taken a physics course before and doesn't know exactly what I mean by the word force, force is how hard something pushes or pulls. So right now, I don't know, that feels like it could be 5 pounds I'm pushing on the table with. If I lean into it a little harder, now I'm pushing on it with a 10-pound force. A complete description of the force. I should stay close to the microphone when I'm talking. I get down to the other end of the table and it probably kind of comes out something like that. A complete description of a force involves not only how hard I'm pushing, but what direction I'm pushing, okay? If 10 pounds toward the south is not the same thing as 10 pounds pushing toward the east. So how hard something pushes or pulls, and the direction that I'm pushing or pulling in. All that information together is the force that either, well, I'm pushing on the table, or what we're going to be interested in is the force with which the rod is pushing or pulling on that ball, electrical forces. If you're a traditional kind of person, the kind who uses an overhead projector instead of a smart classroom, force is measured in pounds. But we are rarely going to use traditional units in this course. It's primarily metric stuff. In the metric system, force is measured in a unit called a Newton, which I defined in some level of detail last fall, but the short version of the story is to say a Newton is a little less than 1/4 of a pound. See unit table and formula handout. For any kind of calculation, okay, on this formula sheet I gave you, the last page, page 8, there's a column that goes down the middle. It says standard SI unit at the top. SI is an abbreviation for international system, or at least it is if you say international system in French. For any kind of calculation, if the numbers you put into the formula are measured in the units listed here, then the answer you get out of the formula will be listed in one of the units, or will be measured in one of the units listed here. So in other words, on the first line it says length, meters. If I give you something in centimeters or kilometers or, heaven forbid, inches, you have to convert it to meters, okay? Time, if I give you something in minutes or hours, you have to convert it into seconds, so on and so on and so on. If you always put the standard unit into your calculation, then you will get the standard unit out. If you stick in a distance measured in centimeters instead of meters, your answer will contain a decimal error. So C unit table and formula handout. M stands for meter, C stands for coulomb. Coulomb's law. If anybody cares about the history, Charles Coulomb came up with this in, I believe it was 1785. I'm pretty sure. If you're going to be on some game show, you might want to double check that just to be sure, but that's what I seem to remember. The force between electrically charged particles. A little picture over here on the right-hand side of the page. Get over here next to the microphone again. Q1 and Q2. Q stands for the amount of charge on each object. This could, for example, be a picture of a hydrogen atom. One of those particles would be a proton, the nucleus, and the other little particle would be the electron. Q1 is the charge on the nucleus, which would be positive 1.6 times 10 to the negative 19. This number up here. The charge on a proton is the same as an electron, except it's positive instead of negative. Incidentally, you can look these kinds of things up on your formula sheet here. The formula sheet does not just contain formulas. That's pretty much what the first few pages are, but you get into the back part, and there are some tables back there where you can look up useful information. So if, just hypothetically, you were to find yourself in the middle of a quiz or exam, needing to know the charge on an electron, it's the first thing on the top of page 6. It doesn't actually say charge on an electron there, it says elementary charge, because actually that number is not only the charge on an electron, it's also the charge on a proton, it's the charge on a muon, it's a charge of a whole bunch of other particles you've never heard of. And anyhow, there's where you can look it up if you need to. So this picture could be a proton and an electron, except the arrows would be pointing the wrong way. It would be an attractive force in that case. Or if I went in the back and got another one of these things, it could be 2 of these pith balls that I've charged up like I did a few minutes ago, sitting next to each other on the table here. Q1 would be the charge on one of them, Q2 would be the charge on the other one. F for force is how hard they're pushing on each other. Or if it was an attractive force, how hard they're pulling on each other. It's the same force on both of them, okay? If this is a uranium nucleus, which has 92 units of charge. There's 92 protons in a uranium nucleus. And the other thing is an electron. So that one particle's got 92 times the charge of the other. The forces are equal, okay? For those of you who have taken the first half of the course, this is an example of Newton's third law, action and reaction. Number one pushes on number two pushes back on number one. They push on each other with equal and opposite forces. So this force that's experienced by both particles is given by this formula. Well, to be precise, the magnitude, how big the force is, the magnitude of the force is given by the formula in the little box there. K is a proportionality constant, which if you're measuring in the SI system, like we pretty much always will, it's just under 9 times 10 to the 9th. I put absolute value signs around the charges because the magnitude of a vector, by definition, is a positive number. The charge Q could be negative, like, for example, in the case of an electron. So that's the reason for the absolute value signs. R, as in, if you're talking about a hydrogen atom, for example, R would be the radius of the electron's orbit as it goes around the nucleus. I think that's probably the reason the letter R usually gets used for that. That's the distance from the one charge to the other, whether they're just sitting on a table or moving around. Q1, Q2 over R squared times this constant. That's the size of the force. As for its direction, well, just keep in mind what it says up near the top of the page, that opposites attract, like charges repel. So, sliding this up a little bit. The way I have the examples numbered may be slightly different on the hard copy you have in front of you, yes. These are the transparencies from when I did the course last year. And I went through and I tweaked a few things here and there, fixed a typo here, put in a new example there. And at some point, I will get around to sending this down to duplicating and getting some new transparencies made. But, as I think I already mentioned earlier, I was not entirely confident that the recordings were going to work with this wireless connection I'm using. And so I kind of waited to see if I'd actually need the transparencies before I had them made. Most of the changes are pretty superficial, but you may see little differences here and there between what's on the screen and what's on the paper in front of you. So anyhow, what I'm going to do is I'm going to run through this one, and then when we get on to partway into the next page, I'm going to have you work on something similar. The terminology I've used is, when I call it an example, that's something I'm just going to write out and talk through it and show you how to do it. And then when I use the word problem instead of example, that's where I'm going to turn around and say, okay, now here's another one, kind of like the one I just did. You do this one. And then I'll give you some time to work on it, because, you know, really the way you get good at something is by doing it yourself. I like to use examples like learning how to swim. You know, you can sit and watch somebody swim up and down a pool on television all day long. Hey, the Olympics, it's cool. Yeah, somebody throws you into a swimming pool after that, you're still going to drown. Okay, the way you get good at something is by doing it yourself. So we'll get to that in a few minutes. But for this one here, I was just going to pick up my piece of chalk. And I get the camera aimed, of course. That just goes over there. I figured out before class that I can't write anything there because of the glare, that it won't show up unless I turn off that light. So we'll just start right about here. Find the force. It's a pretty straightforward problem. You just grab the right equation and throw the numbers into it. You don't even have to do any algebra. But let me just talk for a minute in general about the way to approach many different problems. And again, for those of you who took the course with me last fall, this is going to be sort of a rerun, but I do it this way because not everybody in the room took the course last fall. Before you worry about what the answer is, the first step is to figure out what the question is. And that typically amounts to matching up the numbers with the letters. You look at the formula sheet, and there's all these equations that are full of letters and other mathematical symbols. And then you look at the question, and it doesn't say Q equals this, R equals that. You have to translate from English into mathematics. Especially for a novice who's just starting out, the best thing to do is to lay everything out on paper. Break it into as small of a steps as you can. So not a bad idea in many cases. If you make a little list of what it is you start out knowing, what's given in the question, and what it is you're trying to find. Well, some of the information you have to take off, well, I guess it's in the question also. Sometimes you have to read information off the picture rather than out of the wording of the question. For those of you who don't quite remember how the notation works, the first thing it says at the top of the first page of the formula sheet is that I'm using the letter Q for the amount of charge. Right underneath where it says do not add additional information, one line down, it says Q equals charge. So Q1 and Q2 would be the charges. Actually, I've got the little picture on there too, just like the picture in the notes. So compare that to what's on the formula sheet, and Q's are equal to that. Also, R is the distance from the one charge to the other. And it shows on the picture that that's 20 centimeters. Find the force. Force is F. Well, I didn't exactly write that down specifically. Like I thought F for force maybe was a little more obvious than Q for charge. So find F. Once you've got all your information organized like that, and you know, if it's a simple enough question, maybe you can just do that in your head instead of writing it down, but you want to be fairly methodical about how you approach these things, not only for the sake of keeping yourself organized, but because, like, if it's a test, frequently the name of the game is partial credit. And I want to be able to see that you just simply forgot to copy a minus sign from one line to the next, rather than there's the wrong answer with no explanation. And so lay everything out in glorious detail, both for your own sake and for the guy who's grading your paper. Anyhow, look around the formula sheet, trying to find an equation that contains an F and these other things on the list and nothing else. And in this case, that would be Coulomb's law. drop in the numbers. Coulomb's law constant is a universal constant. That's always going to be the same thing. This number has a whole big glob of units on it. Newtons times meters squared per coulomb squared. And then for the rest of it, if you stick the numbers in just the way they're written over there, there's a problem. The problem is that the units are inconsistent. This is like I was saying 5 or 10 minutes ago about how there's that column in the table of units on the formula sheet. Always put the standard units in and you'll get the standard units out. Well, this is the details of how that works. You've got meters there. You've got centimeters there. That's inconsistent. Likewise, with the units for charge, you've got coulombs there, but microcoulombs here, also inconsistent. For that, so before you get out your calculator, you got to clean that up. If you don't remember all of the metric prefixes, that's in the reference handout also. I think it was the next to the last page. Yeah, bottom of page 7. Everything from the prefix for 10 to the negative 24 all the way through the prefix for 10 to the positive 24. So there's some pretty obscure stuff there, but micro actually gets used quite a lot, at least in my world. So if you don't happen to remember, you look there, you see the symbol, the Greek letter mu, which stands for micro, like it says next to it, and to the left of that, 10 to the minus 6. So that little symbol there means 10 to the minus 6. Write 10 to the minus 6 where that little symbol used to be. So 4 times 10 to the negative 6 coulombs for micro coulombs. Likewise, 3 micro coulombs. Micro means 10 to the negative 6. You see how it works now. Units can be manipulated according to the same arithmetic rules that you do with numbers, okay? So just like if you had 7 times 7 over 7 squared, that would just cancel out. Well, units work the same way. Coulombs times coulombs divided by coulombs squared, they all cancel each other out. If they're all in coulombs, which is the reason you have to convert. Likewise, centimeters has to be changed into meters. When you square the number, the unit gets squared also. So you've got square meters down here, which cancels with the square meters up there. So the only surviving unit that doesn't get canceled out is newtons. The force comes out with the unit of force on it, which is how things are supposed to work. When you run all the numbers through your calculator, they come out 2.7. Units work out to newtons. And yes, another way I'm a dinosaur, aside from using an overhead projector, is I still write in cursive. For those of you who can't read it, it says, notice, units are manipulated like numbers, like the way I canceled them out up here. Now, a complete description of a force includes its direction, as well as how many newtons it is. And just shift the camera over again a little bit. Incidentally, for anybody who enjoyed this so much that you just want to run right out and watch it over again right after class, you might have to wait a little bit. I mean, you know, it's a 3-hour class. You put it all, well, I usually pause it during sample problems, but if I run it for the whole 3 hours, it's over a gigabyte. And it takes the system a while to process that. So if I just go back up to my office after class and go to post it in Blackboard, it's not ready yet. If I think of it about 7:30 this evening, after I finished my dinner, it's probably ready by then, if I think of it. If I don't, might be sometime tomorrow morning by the time that. Once in a great while, somebody comes into my office and says, I wanted to watch that video and it's not up yet. It's like, oh, I meant to do that 2 days ago. So if it's been more than a couple hours and you want to see it, you know, send me an email or come yell at me or something. But it will take a couple hours to get this posted at the minimum. So the direction. Well, one of them's got a minus sign on it. The other one's got a plus sign on it. Opposites attract. The question is asking about the object on the left, the one whose charge is -3. It's going to be attracted to the positive charge, which means the direction is to the right. It's being pulled toward the right. If the question was, what is the force on the 4 microcoulomb charge, then the answer would have been 2.7 newtons toward the left. But that wasn't the question. The question was, what is the force on the -3? Now, let's see, next thing I've got there is I put in a little comment about why I make you take notes yourself. I think I already said that a while ago, actually. So we go to the next page. Put standard units in to get the standard units out. Yeah, that's something else I already said. Complete answer includes the unit. If this was a quiz and you wrote down 2.7 toward the right, that would get you 9.5 out of 10. The unit matters, okay? If a weight's going to fall on your foot, it makes a lot of difference whether it's 3 ounces or 3 tons. The 3 by itself is meaningless if you don't have a unit on it. So get in the habit of labeling the units on things. For one thing, if you're paying attention to the units, that keeps you from making the kinds of decimal errors I was just talking about here. If you aren't thinking about the fact that these are microcoulombs rather than coulombs, you're going to be off by a factor of 1,000,000 there, and you're going to be off by another factor of 1,000,000 there. Well, you know, what's a factor of 1 trillion between friends, right? you need to keep an eye on the units on things, and that includes labeling it on your answer. An example of converting units. Not that we're really going to use pounds very much at all in this course, but just as a little exercise, 2.7 newtons, what would that be in pounds? I call that number 2 in the revised version. Well, before I mean, it only takes a moment to write it out, but before I do that, explaining what I'm doing, to convert units. Well, this goes back to the same idea here about how units can be manipulated the same way that numbers are. If you're just playing around with numbers, you can multiply something by a fraction where the top is equal to the bottom. And when you're done, you'll have the same thing, right? If I took this 2.7 newtons and I multiplied it by 9/9, that's just a 1. And I'd still have 2.7 newtons afterward. This is still true in a sense if you do something like this. Say you're talking about how fast somebody's car is going, 70 miles per hour. And you wanted it in miles per minute instead. Well, everybody knows there's 60 minutes in an hour, but the question is, should you multiply by 60 or should you divide by 60? Well, the way you figure that out is by canceling units. 1 hour equals 60 minutes. So you've got a fraction where the top is equal to the bottom. Not numerically equal, so you're not going to have the same number when you're done. But it's physically equal. 1 hour means the same amount of time as 60 minutes. So you'll have something that physically means the same thing when you're done. Hours is on the bottom in miles per hour, which is how you know you want hours on top in your conversion factor, because hours over hours will cancel out, leaving you with miles per minute. Just as a comparison, if you did it the other way around, multiplying by 60 instead of dividing, then the units come out mile minutes per hour squared, which is not how any sane person would describe the speed of a car. Okay, so that's how you can tell. I mean, you know, minutes to hours, that's a fairly familiar thing, but when it's something like converting horsepower into watts or, you know, something like that, you can look up the conversion factor on the last page of the formula sheet where that table of units is. But once you've looked up the conversion factor, do you multiply by that or do you divide by that? And this is how you figure it out, canceling out units. So in this case here, we've got 2.7 newtons. And referring to page 10 of your reference, or page 8 of your reference handout, if you go down a few lines to where it says force, it says 1 Newton equals 0.2248 of a pound. Well, you know, I went to 4 digits just in case anybody really wants to be careful and precise, but well, it takes less time to write 3 digits, so I'll just round it off a little bit. 0.225 pounds equals 1 Newton. And where I got that from, once again, is I looked it up on that last page of the formula sheet. So you take the 2.7 newtons, you multiply by a fraction where the top is equal to the bottom, 0.225 of a pound equals 1 Newton. You set that fraction up in a way that makes the unwanted unit cancel out. newtons divided by newtons leaves you with pounds. And that's how you decide that you should multiply by that number, not divide by it. So, I've shown you all of that. Should be enlightened enough to do this problem here, which I think was actually called problem number 3 on the version of the notes you've got in front of you. And I will pause this because we don't need a lot of dead time recording. Okay. So find the force. Start out with the magnitude of the force. In other words, how big is it? Get that from Coulomb's law. K times the product of the charges, absolute values to be precise, although in this case they're both positive, so I guess I don't really need the absolute value signs. But one of the charges is 2 microcoulombs, 2 times 10 to the negative 6 of a coulomb. And the other one is 3 times 10 to the negative 6 of a coulomb. And the distance between them, you got to convert centimeters into meters. 0.1 of a meter. Don't forget to square it. That'll give you a decimal error also. People do that more often than you might think. 5.39. For the magnitude of the force on both charges. For the direction, well, they're both positive. Like charges repel each other. Like charges repel. So that one's going to get pushed that way, and that one's going to get pushed that way. So the answers are part A, the 2 microcoulombs, that's the one on the left. That's this one over here. So the direction on that one is it's being pushed toward the left. 5.39 toward the left. That's the answer to part A. Part B, the force on the one on the right, that's this one over here, that's the same amount of force, but opposite direction. And then unit conversion, it's the same sort of thing as this one that I did over here. You're going to multiply by the 0.225. Multiply by a conversion factor where the top is equal to the bottom, set up in a way that makes the unwanted unit cancel. 2, 1. Little terminology. Vectors versus scalars. Physics is all about measurable quantities, things like velocity and acceleration and pressure and volume, and in this case, forces. And these measurable quantities come in two varieties called vectors and scalars. The difference is some things have a direction and some things don't. Force is a vector because to completely describe the force, I not only have to say how big it is, I have to say whether it points left or right or up or down or whichever way it points. Velocity is a vector. If you're driving in your car at 30 miles an hour, 30 miles an hour toward the east is different than 30 miles an hour toward the north. Other things do not have a direction. Time is a scalar. If I've been talking about this for 2 minutes now, it's just 2 minutes. It's not 2 minutes toward the east or 2 minutes toward the left. Temperature is a scalar. How warm is it in this room? There's no direction to that. Pressure is a scalar. Mass is a scalar. So electric charge is a scalar. It has no direction. It's just, well, it's basically how many electrons did I put on the rod? It's just times, some conversion factor to make it into coulombs. It's just how much there is. There's no direction to it. So vectors, when I throw these words around, that's what they mean. Vectors have both a magnitude and direction. Scalars have only a magnitude. A significant part of Physics 121 was showing you, giving you practice doing vector arithmetic, all that stuff about components and sines and cosines. And yeah, that's the thing we had to sacrifice in order to make it so that the first course is not a prerequisite for the second course. In this course, I will stick to one-dimensional questions where the direction is just simply a plus or a minus sign. It's to the right or it's toward the left. It's not going to be at a 24-degree angle, because if it was, I'd have to go back through all that stuff that I spent a lot of time already doing in the first course. So you probably are glad to hear that, I'm guessing. But anyhow, you might just keep in the back of your mind that in a full-blown 2- or 3-dimensional treatment, all of that stuff about vector addition that most of you have already seen would come into play. You'd have to express the electric fields or the electric forces or whatever in terms of their components and add up the x components and add up the y components and do all that stuff. Names of vectors are indicated by having an arrow over the top. So F with the arrow over the top is referring to the force that I'm calling F, perhaps 23 newtons at 14 degrees above the horizontal. When you get into the subtleties of the notation, if you don't draw the little arrow over the top, that refers to just the magnitude of the vector. Just the 23 newtons, I don't care about the 14 degrees. Or maybe for a little extra emphasis, put some absolute value signs on there. That's another notation that means the same thing. Okay. Slide this up a little bit. So back to this situation again. That all charged up real nice. And yeah, the rod is able to exert a force on that ball without touching it. No matter what I do, I can't get it any closer than, I don't think I can even get it an inch away. It's usually 1.5 inches or 2 inches. So how does that work? I mean, if I want to exert a force on you, I can't do that with me here and you there. Something has to transmit the force. If I want to knock you out of your chair, I've got to have like a big long 2x4 or something like that to poke you with to get the force from me to you. So there must be some invisible something around this rod that transmits the force that it's pushing on that hanging ball with some kind of an invisible 2x4 or something. Well, we call this invisible influence an electric field, very similar to the gravitational fields that you're all familiar with from everyday life. I think probably everybody in the room at some point in their life has jumped up in the air and noticed that they came back down again. The earth is able to pull on you without actually touching you, because the earth creates this invisible influence around itself that we call a gravitational field. And this is pretty much the same story. It's just rather than a gravitational field, it's an electric field. It's another example of the same kind of thing. So charged objects create an invisible influence around themselves called an electric field. One way to describe its strength is with the electric field vector, the force per unit charge, E equals F over Q. So you've got something creating a field, like this rod, and some kind of a test charge that you're using to observe the effects of that field. So I got my test charge on the end of the string here, and I notice that when I bring it near the rod, there's a force, and I can tell there's a force because the string leans to the side. Over here where the field is weak, it leans only a little bit to the side. Closer where the field is stronger, it leans at a sharper angle. So the amount of force on that test charge is a way of observing the strength of the field, but the force on that ball there depends not only on the strength of the field, it depends on how charged up that ball is. Also, if I get twice as many electrons on that ball, it's going to lean twice as far away in the same field. The force per unit charge, twice the force when you've got twice as much charge, the force per unit charge would be something that's a property of the field only, independent of the thing that you're exploring the field with. So E equals F over Q. The test charge that you use is conventionally thought of as being positive. I mean, you have to make one choice or the other. And the way it's traditionally done is to say that the direction of the electric field is the direction of the force on a positive charge. If you put a negative charge like an electron in the field, well, if you want to make a gravitational analogy, it would be as if there were two kinds of staplers, okay? There's the kind where when I let go of it, it goes down. And then there's the other kind where when I let go of it, it goes up. Now, gravity doesn't work that way. There's no such thing as a negative mass. But electricity does work that way. There are negative charges. So what am I going to say is the direction of the gravitational field? The direction that the one kind of stapler goes, or the direction that the other kind of stapler goes? Well, I have to pick one, and we're going to say it's the kind that goes down. And in sort of a similar way, we define the direction of the field to be the direction that a positive charge would get pulled. So the electric field, like if the field is created by a set of charged metal plates like that, and you hook it up to some power supply or something or you charge it up by rubbing it on something like I was doing here today, there's going to be an electric field between these plates, and that field will point from plus to minus. Because if you put a positive charge in that field, it would be repelled by this positive metal plate, and it would be attracted to this negative metal plate. And so the force on a positive charge is in the direction of these arrows I drew. If you put an electron in there, since it's negative, it would get pulled the other way. So electric field, plus or minus. Well, 3-hour class, I always like to put a break in the middle so that, we don't have people passing out from exhaustion or something like that. And it's just about dead center in the period now. So 10 minutes. I'll start up again about 5 or 6 after.